Okay. Now, in the next couple of modules, I want to talk about one of the most favorite excited state processes, personal favorites for me, partially because half of my PhD thesis was on this, and we have done a lot of work on this process, and this process is excited state proton transfer. We have already talked a little bit about that, but I realized that we have presented it in bits and pieces over several modules. So, at the risk of repeating some things that we have discussed already, we are going to do a very brief recap at the beginning, and then in this module we will only provide an introduction. Second part of the real ESPT, there is no ultrafast dynamics here. In fact, we are going to present an ancient paper from 40 years ago, because it is still relevant. It still tells you how one can approach a problem of understanding photophysics. In the next module, I want to present a debate that raged for 10 years about the exact mechanism of excited state proton transfer, intermolecular proton transfer in 7-aza-indole dimers. So, this is something that I must have said in one of the modules earlier. The reactivity in excited state is different from that of ground state, and that is because as chemists we know that electronic configuration is different, and it is electronic configuration that determines reactivity. So, if you look at the ground state, this is the electron configuration HOMO 2 LUMO 0. This is well, in first approximation the electron configuration of these S1 state. I say first approximation because I have just drawn arrows, I have not written the spin wave function alpha beta minus beta alpha. And then this is a triplet state where you once again have one electron in HOMO, one in LUMO, but spin wave functions are different. This is how in a first approximation you draw it. So, all these states have different reactivity, and this is, as we have said earlier, this lies at the heart of excited state processes, because since excited state electron configuration is different, reactivity is also different. So, many reactions or chemical processes that do not take place in the ground state can take place when the molecule is excited. So, we generally do things better when we are excited, molecules do the same. Usually they work better when they are excited. And as we said earlier, photoacidity is something that arises from there. Organic acids are more acidic in the excited state, organic bases are more basic. And the example we took was that of phenols. Everybody knows that phenols are acidic because the phenoxide ion that is produced as a result of deprotonation is stabilized because of delocalization of the electron cloud on oxygen over the ring. And if you think of this from the MO picture, this is what it is. Let us think of simple phenol. The molecular orbital energy diagram of benzene is like this. So, the 3 bonding orbitals are all occupied. When the electron cloud from oxygen has to get delocalized over the ring, then the electron clouds have to be accommodated in one of the higher energy antibonding orbitals, and that is what happens. That is an important role antibonding orbitals play. Sometimes while studying MO theory, we think that antibonding orbitals are useless. They are not. They have important roles to play. SN2 reactions, for example, make use of antibonding orbitals. Here we see another example of use of antibonding orbitals, and all of us would have studied this carbonyl complexes, where again antibonding orbitals which are heavily displaced towards carbon atom are used to accommodate electron cloud coming back from the central metal atom, and that is what gives rise to this synergistic effect. So, here the electron cloud is accommodated in well, ground state in the antibonding orbitals. That is why phenol is acidic. However, if we perform a pi star excitation, for example, then a vacancy is created in the lower lying bonding pi orbitals, and now the incoming electron cloud can be accommodated in lower energy MOs, bonding MOs, rather than antibonding MOs. The consequent stabilization is the driving force for enhanced acidity in the excited state. And once again, the favorite example I have in the, well, this same thing happens for anions. To demonstrate this, the favorite example I have, all this is taken from your Lakovich's book, is that of beta naphthol. one can generate titration curves using absorption spectrum to get the ground state pKa, or from the fluorescence spectrum to get excited state pKa. It turns out that pKa for beta naphthol in ground state is 9.2, whereas in excited state is 2. So, shift in pKa by 7 units is a huge amount. So, we are talking about a change in 7 orders of magnitude of proton concentration, in which the molecule beta naphthol can give up a proton. So, if you take beta naphthol in say neutral solution pH 7.4, it is not going to lose a proton, it is going to remain in protonated state, but if you excite it with light of appropriate wavelength, then you can actually release the proton, making beta naphthol a photoacid. So, this has several applications. One thing that has been done to trigger many biological processes is a pH jump. So, use a photoacid in water, you excite it, proton is lost. So, as a result of excitation, proton concentration goes up, and if you do this excitation using pulse light, then proton concentration goes up all of a sudden. Okay. So, if you have an acid catalyzed reaction, then that is your time 0, the time of excitation. That is when the acidity is switched on, like dipole was switched on in solvation dynamics, and the reaction starts. So, you can now start following the kinetics of this reaction. So, you can follow very, very fast acid catalyzed or base catalyzed reactions using this method of photoexcitation, using photoacids if it is acid catalyzed. And one experiment that has been done, a very elegant experiment using a photoacid we have discussed already, is the mechanism of sequential proton transfer through water bridges in acid base reactions. I did not give all the references last time, so let me make up now. If you are interested in learning about this, these are the papers that you can study. You can see Biochemistry, science, science, science. So, the reason why so many papers have been published in science in this is that it is a very fundamental question. So, if you can provide an answer to a question that has stayed on for a long time, then it is highly interesting, and that is what mainly Niebering's group and to some extent Johnson's group had done. And this is something again I did not say last time, and then I felt that this discussion is incomplete if I do not at least mention them. So, in our kind of experiments, actually it is important to know theory, understand theory, be aware of what has been done by theoretical chemists. Otherwise, it is not possible to make much of progress. So, to do experiments, one cannot be afraid of reading papers of computational chemistry or molecular dynamics simulation, StatMech and so on and so forth. If you are going to do good theory, you cannot be afraid of reading experimental papers. They actually are synergistic, go hand in hand. So, the theoretical model, that is the models that are very important here, you see all of them have the name of one person, and that is Smoluchowski. Smoluchowski, you might have read Smoluchowski's name in some other context, but his work was mainly in the liquid phase. So, to understand how proton gets transferred through a hydrogen bonded network, as you are talking about hydrogen bonded network, that is a connection with what we did in the last module. There also it was how energy gets transferred in a hydrogen bonded network. So, here Smoluchowski's model was for diffusion assisted colloidal aggregation. Then in the next step, this Debye-Smoluchowski model dealt with this potential of mean force method to address the same problem. And Smoluchowski, Collins, Kimball model, of course, names I am taking, they are all stalwarts. I think everybody has heard these names. Anybody who has done MSc physical chemistry would definitely have at least heard these names, if not have studied their work. So, there has been a continuous improvement in theoretical studies in this context, and a very celebrated model that existed already is this Eigenvalor model. So, you see that experimental results of neighboring that I showed you earlier, and I am going to show you in a few minutes once again, that did not fall from the sky, because they already knew that this eigenvalor model existed. Remember, I had talked about encounter stage and all that was actually predicted theoretically. So, again there is a diffusion stage in which you have, this is the acid, this is the base. In the diffusion stage, the acid and base come together and form the reactive complex. And then in the encounter stage or reaction stage, this reversible reaction takes place, which involves protonation, deprotonation. And in the third stage, the proton transfer species have to diffuse apart. Okay. If this stops at encounter stage, then what will happen? Then some proton will be transferred, some will not be transferred. So, finally, you do not really get that acid base reaction to that extent. So, it is this diffusion in and diffusion out, they are naturally going to be very important in this entire process. So, this is eigenvalor model. We are showing you only this schematic, but of course, to develop the model, that is very detailed, a lot of work went into that. And the most important extract from there that we can take is that the intrinsic proton transfer here, that is our 10 picosecond per molar, okay, very fast ones. That is why you need ultrafast. So, to study this, ultrafast UV pump, IR probe, and IR pump, IR probe, both have been done. Okay. Previously, I gave you the impression that only UV pump, IR probe was done. That is not the case, both were actually done. Okay. So, and the acid, photoacid that we used, I will go a little fast on this part, because we have presented this already, is this pyranine. So, the decay of the photoacid band is 1486 centimeter inverse, rise of the photobase is the anion, corresponding anion after loss of proton, that is at 1435 centimeter inverse. If you follow this, you get to know the deprotonation dynamics. CO stretching mode of acetic acid is at 1720 centimeter inverse. So, the base that is used is acetate, right. So, when acetate becomes acetic acid, then this 1720 centimeter inverse stretch should show a rise time. That gives you the dynamics of protonation of acetate. Here it is written deuteration, because they are actually used a deuterated photoacid, because then the signals are easier to see. So, as we said earlier, in a high concentration, we see that these dynamics are same, at low concentration they are different. That is where this diffusion comes in. I have already shown you this data, and this one is a little more detailed than what we showed earlier. There, here the numbers are actually mentioned. So, by analyzing the data, they could work out all the time constants. And then what they found is that when you talk about water breach, and this is an important thing, this is another reason why I wanted to show you this explicitly once at least. There has been a lot of work on what kind of associated states protons exist in water, and even now people do contest these things. But it is largely believed, what we talk about always is H3O plus, right. But why will it stop at H3O plus? After all, you look at this first one, this is oxygen, hydrogen, 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 that is H3O plus. That can get hydrogen bonded to another water molecule, right. So, this kind of a cation where H3O plus is hydrogen bonded to a molecule, to another water molecule, that is called Zundel cation. And the second one, where each, so you can see the central moiety here is H3O plus, where H3O plus is hydrogen bonded to not 1 but 3 water molecules, that is called the eigencation. And as you can perhaps understand, these two ions would have different IR frequencies, their stretches would have different IR frequencies. So, by looking very carefully at the IR spectra, what you see is that you get this D3O plus signal going down, you get something rising here. So, a careful analysis reveals that this eigencation can be detected actually. So, when you form that encounter stage, you do get an eigencation, and hence this mechanism was elucidated. Okay, so that is the revision that I wanted to do quickly. Now, let us move on to the introduction of excited state proton transfer. So, the thing is this, suppose we said that upon photo excitation organic acids become more acidic, organic bases become more basic. Now, suppose in a molecule we have an organic acid as well as an organic basic group. We have phenolic OH and we have a nitrogen, imidazole nitrogen or something. Then what will happen? This is the situation, this is the organic acid group, this is the organic base group and there is hydrogen bonding. You shine light, there is proton transfer. And this proton transfer takes place within the molecule itself. In that case, it is called excited state intramolecular proton transfer, and this is an example of a molecule where excited state intramolecular proton transfer takes place. Now, if you have two molecules coming close together, you can have intermolecular proton transfer as well. And for intermolecular proton transfer, the kind of molecules that have been studied very extensively, this is not really 7-azide-indole dimer. I will discuss 7-azide-indole next day, but it is very close. So, does this remind you of something, this kind of a structure where you have two molecules that are hydrogen bonded to each other and form a pair of molecules? Generally, they remind us of hydrogen bonded base pairs of DNA. So, the claim to fame of 7-azide-indole primarily is that it is supposed to be a good model of hydrogen bonded base pair ATGC of DNAs. So, we will come back to the actual 7-azide-indole problem next day. But now, let me present to you this piece of paper which I am very fond of. As you can see, it was published in 1979, long ago, 40 years ago, and this is actually a remarkable paper. Kasha is the legendary Kasha, Michael Kasha of fluorescence spectroscopy. Sengupta became a professor in Pradeep Kumar Sengupta, he became a professor in Shah Institute of Nuclear Physics. He retired about 10 years ago, 9 years ago. And so you can understand, it's 1979. So, they did not really have the instruments that we have today. So, what I am going to present in the next few minutes is actually all steady state data. No ultrafast, no time resolved even, because it is important to understand the steady state spectra before you can go into time resolved data. So, see the reason why people got interested in 3-hydroxyflavone, 3-hydroxyflavone is a natural product and all, is that look at the absorption spectrum. Well, you can only look at it, you cannot read at the x axis unfortunately, but I will just tell you this absorption is in UV, this colorless compound, but emission is in the green, 297 Kelvin room temperature, emission is in the green. So, you have a molecule that you excite at UV, high energy, and it emits in the green, which is considerably lower energy. Why? As we have studied earlier, one of the most prominent signatures of excited state processes is Stokes shift, and here we definitely have a Stokes shift. And the one that what is not shown here is that the excitation spectrum matches the absorption spectrum. So, the Stokes shift is not due to presence of some impurity. So, why does this happen? To explain this, and that is the time when ESPT was being discussed for the first time through the works of Feller and all. So, what they looked at the structure, this is a structure ground state that is established, and you can see there is a phenolic OH and there is a carbonyl group oxygen. So, one might expect that upon excitation this proton goes from this oxygen to this oxygen, and from this ground state normal form it forms a tautomeric form in the excited state. We will have more to say about the energy diagram shortly, but if this is the model, then the next piece of data already in front of you is this. The experiment that was done is you look at the spectrum at low temperature, nitrogen, liquid nitrogen temperature 77 Kelvin, and then immediately you see a blue shift. There is hardly anything that resembles the room temperature emission spectrum. The entire emission moves to blue, and now look at this spectrum. Unfortunately, they might not have had, of course, they did not have computers like we have today. So, normalization and all were not done, but look at this spectrum, forget about the first part, look at these bands and look at this band structure. Do not they look like mirror images? Yeah. So, at liquid nitrogen, the spectrum that you see is for the locally excited state at liquid nitrogen temperature. So, if this is the ground state, the emission at 77 Kelvin is due to the corresponding locally excited state N star, and in the at room temperature, the Stokes shifted one is due to the proton transferred tautomeric state. Okay. Of course, it is only logical to ask who has told you it is proton transfer, and that is addressed shortly. Some excited state process is there, right. So, we can say that this is emission from the Frank Condon state, this is the emission from the nascent state, the one that is formed by excited state process. So, what would the energy diagram look like? So, from the absorption spectrum here, there is no signature of the ground state corresponding to this green emission excited state. Yeah. So, the energy of the N form has to be significantly lower than energy of T form, right. So, you get what is called a double well potential. What happens in excited state? In excited state, you see at room temperature emission is exclusively from T star. That means in excited state, T star must have lower energy than N star. Yeah. So, again you have a double well potential. Let me, so what I am saying is this, in ground state, this is the energy of N, let us say, x axis, so this is energy, y axis, x axis is a reaction coordinate, I can write R, yeah, this is N, and energy of T must be higher, right. So, this is double well, and then see, okay, we will come back to that. In the excited state, however, this would be the energy surface for N star, energy surface for T must be lower in energy, right. So, this energy gap is naturally much higher than this energy gap. So, that is why T star fluoresces in green, N star fluoresces in blue, all right. Now, to complete the picture, I will draw this reaction barriers. How do you get the barriers? Because there is some curve crossing and mixing of these two. How do I know there is a barrier? Because I could have drawn a diagram like this. This is N star, this is T star. Why am I saying that this is not the case and this is the case? Because there is a temperature effect. If the barrier is sufficiently high, then what will happen? At low temperature, the molecule cannot cross and you will see emission exclusively from N star, that is what is happening. If there is no barrier, then even at 77 Kelvin, you should see some T star emission. Yeah. So, the effect of temperature that is present there tells us that this is an activated process. So, this is how the energy diagram turned out to be. Okay, so, what do we have? This is one well, this is one well, double well potential. Here also double well potential. Double well potentials can be of two types. If the energy minima are same, then it is called symmetric double well potential. If they are not same, then you call them asymmetric double well potential. Okay. And here you see, so this is the diagram that was drawn. So, you have asymmetric double well potentials in ground as well as excited state, and when you go from ground state to excited state, the asymmetry is reversed. Okay, reversed asymmetry is there. So, this is the schematic that was drawn, and later on plenty of calculations have been done to prove that this is correct. Now, we come back to the question, who has said that this is a proton transfer and not something else? To do that, experiments were done in methanol and deuterated methanol. So, if it is a proton transfer and if the and here of course, there is a catch, but we will come to that. So, if it is a proton transfer and the reaction coordinate is the proton transfer coordinate, that is the important part, then you should see this primary kinetic effect, primary kinetic isotope effect. right. So, you should see more of proton transfer in methanol than in deuterated methanol, because deuterium is heavier, and that is what happens. These are the emission spectra. Achha, by the way, this is 2-methyl butane, something very close to our 3-methyl pentane, non-polar, and this is methanol and MEOD. Why these particular solvents? Because you are going down to 77 Kelvin, you cannot work with water, you cannot work with acetonitrile, because you need a solvent that forms glass, it will remain transparent and does not become hazy at low temperature. So, methanol, ethanol, methanol-ethanol mixtures, 2-methyl butane, 3-methyl pentane, these are some solvents that form glasses, and depending on your experiment you might want a polar glass or a non-polar glass. So, earlier it was polar, non-polar, now it is polar. So, here you see the ratio of N to T peak, N star to T star band is more in methanol than in deuterated methanol, right. That is why we get an indication that it is proton transfer in the excited state, and proton transfer is the reaction coordinate. Why I am saying this? Because later on it has been shown that for many proton transfer reactions you do not see a kinetic isotope effect. That is because that is not the reaction coordinate. Remember, the slowest process determines the rate of the reaction. So, suppose the molecule is such that this is your OH group and this is your proton accepting group, okay. They are in some kind of an orientation where they are not close, and it requires a conformation and relaxation to bring the OH group close to the proton accepting group. Then this conformational relaxation becomes the reaction coordinate, okay. So, at that time you do not see any effect of protonation, because how much time it takes for this to take place, that is what determines the rate. Compared to that, this proton transfer is so fast that you do not see an isotope effect. Fortunately, in this case the molecule is planar, right, no question of any relaxation that is required. So, proton transfer is the reaction coordinate and you see a primary kinetic isotope effect. Okay. Of course, we are showing you only the one of the earliest works in this molecule, there have been many later on. Okay. So, proton transfer is established, but the spectra bring up a new question. Remember what the spectrum was like in the non-polar solvent? Room temperature? Single band, right, green emission. What is the spectrum like? These are all room temperature spectra. Here in methanol or deuterated methanol, you see 2 bands instead of 1. So, normal peak, normal band, which is not there in non-polar solvents, why does it show up in protic solvent? And well, this is another reason why I like this paper so much, because it introduces you to many important factors in proton transfer. Well, what happens in hydrogen bonding solvents is that you can, of course, you will get hydrogen bonding with your solvents all around. So, you get this kind of block structures. Block structure means your OH proton, even though it is also believed that if there is an internal intermolecular hydrogen bond, if there is a possibility of that, then intermolecular hydrogen bond will not be formed, but they may not hold in liquids due to sheer number of solvent molecules present around a solid molecule. So, this kind of structure. So, just look at this. If there is a hydrogen bonding between this carbonyl oxygen and a neighboring alcohol molecule, then what will happen? It will be difficult for it to take to hydrogen bond with another proton and accept it. So, block structures hinder ESIPT, that is something that is known. And this is an example of block structures. Again, I am very fond of this paper because this is my first published paper. The molecule is HPBI. This small band that you see is due to the normal form, this is due to tautomeric form. Here what happens is this molecule exists in different tautomers. So, you always get 2 bands. Here what happens, here when the molecule is incorporated in micelles, you see there is a rise in tautomer, that is because it is protected from water and you have fewer block structures. Tautomer emission is enhanced. But do not think that hydrogen bonding is always the villain. sometimes it can be hero as well. There are plenty of examples. This molecule has been studied extensively by this group of Flor Rodriguez Prieto, and then we have done some work of this in confined media, a lot of work of this family, pyridyl benzimidazoles. Here the geometry of the molecule is such that you need a H3O plus bridge for the proton transfer to take place. So, if you do not have this hydrogen intermolecular hydrogen bonding with solvents, then there is no ESIBT. So, it can work both ways, right. To conclude, we have introduced this concept of excited state proton transfer, intramolecular and intermolecular, and we have discussed some of the salient factors that have a role to play in its dynamics. So, next day we are going to talk about this celebrated debate of intermolecular excited state intermolecular double proton transfer ESIDPT in 7-aza-indole dimers, and that is going to teach us how careful one has to be while analyzing ultrafast dynamics data, because here we have an example of a Nobel laureate going wrong. And it also takes us to another important concept. In fluorescence spectroscopy, we always go by Kasha rule, and we think Kasha rule is always correct. Maybe as a prelude to the 7-aza-indole problem, we will discuss to what extent Kasha rule is correct when you look at time evolution of emission spectra. Okay? That is what we will do in the next module.